Let's continue to building the components for our database first. And as I said, we're going to use SQL as a guide and build as many components here as we can. Okay? Once we understand how SQL statement execute and what we need to manage that SQL statement, then we'll talk about the rest of the architecture, which are the supporting cast, to make sure that we can execute the SQL statements efficiently even in the future as SQL statement comes. So I'm going to make a little room here, so hopefully everybody can follow me. Take that out. All right. Now, we're going to start with a basic select statement. So here is a select, let's say column 1, column 2, from table 1, where column 1 greater than value, and I don't know, we can add a few items here like group by column 1, comma, column 2, okay, and then for example order by column 2. So this is a basic, a very basic select statement that is reading from one table, has a very simple where clause and a simple grouping. Now, SQL is designed to resemble English. That will make writing it easy. That will make writing and relating to general public questions easy. So writing SQL as an English helps developers to better understand and be able to relate their code to what the actual end user wants. Okay? However, of course, written this way, it is not executed the same way. To execute this statement, of course, the statement has to be taken apart and be put in the logical steps. Then extract information about each step and find the best plan to get this result set. So what is the first thing I need to look in here? The first thing we need to do is we need to be able to assign an ID to a SQL. As we said, each SQL is going to be assigned a package that is called a cursor. Okay? That is the execution plan for each SQL. Now, that cursor can be reused, as we talked about, and can be shared by multiple sessions. Therefore, if I can identify the SQL statement, if the SQL statement is reused, then I can also identify that and then have them share the same plan. Therefore, every SQL is assigned a SQL ID. Now, SQL ID must describe this statement uniquely. Therefore, when the statement is submitted to the database, the client sends the statement through connection. So the server process, after the connection is established, is communicating to that user process. So the server process will send the SQL to that server process. Server process submits the SQL to the database. First thing database does has to go through the syntax and make sure the syntax is good. And guess what? Syntax is the best way to identify SQL. Because if the SQL is identical, the syntax will be exactly the same. Now, in Oracle, SQL is actually case sensitive. So SQL that is written on a different type of casing, white spaces, when they're used, for example, before and after equal signs, before and after greater than, less than signs, things like that. All of those add up to the SQL ID. Okay, so it's very important if we want our SQL to be shared, generating the same SQL. All right, so here, as we go through, the statement, we use a utility that is called a parser. Parser's job is to check syntax and generate that SQL ID. So once the parser needs to go and look at the statement, parse the statement, figure out that all of the statement format is good and there is no syntax problem. Now, we also call plan generation parsing in Oracle database or in many databases. So the process that generates the plan is also called parsing. That is a big process, and checking syntax is the first part of that process. Matter of fact, it enters me into the process by giving me a SQL ID where the SQL can be identified. Therefore, I can start on managing the plan. Okay? Now, parser is a utility that does the syntax check. However, the actual parsing and plan generation of the statement is done by another utility that is called the optimizer. The optimizer will collect the stats for the table, okay, to be able to understand how the data is distributed in the table. For example, when the column 1 is greater than this value, how many rows are going to come back? If I'm going to return a lot of the table, many rows from the table, then I might as well read the whole table. If I'm going to return a few rows from the table, then maybe I can use some pointers that can tell me where those rows are located. So I can only retrieve the minimal data I need for the statement. So how do I go get statistics? And as part of getting the stats, we also want to validate that the user has privilege to execute the statement. Therefore, the first thing that needs to be parsed would be the table, okay? By understanding the from clause first, now we know which table, we know who to get the metadata for, and we also know which table to get all of the statistical information for. Therefore, now that I read and bring all of the stats and the information about the table, this is called the metadata. Okay, it's data about data. It's the statistical information, the supporting data in how these tables are being managed. I need to write that information again in memory, because if Ron using application HR and accessing the table employees, another employee, John, may also use application HR to access table employees. Therefore, the metadata that I load is also I/O, so might as well be shared. So here in the SGA, in our shared area, we have a component called the shared pool. Shared pool, we said this is the pool of SQL statements that the users can share. Therefore, we put in the shared pool all of the specific information we want to use to manage SQLs. One of the components here is called a data dictionary cache. Data dictionary is where we hold all of our metadata. Therefore, when the optimizer needs the metadata about the object, we will read these data dictionary rows and load them here. And since now it is in the shared memory, other users can also have access to that same metadata. All right? So now we got the metadata, we understand the table structure. What is the second thing we need to do to manage the plan? The second thing we need to execute and understand is how the data is distributed, how many rows we need to return. And that's based on our condition, our where clause. Therefore, the second thing I need to do is look at the statistics that we brought from here and then see what other child objects may exist. Do we have indexes that I can get pointers from and retrieve the data? Okay, so after we look at the stat and the data distribution and how many rows are going to be returned, the next thing we're going to look at is the groupings. Now that the data is returned, I need to make sure that the data can properly get grouped. However, take a look at this. To group, I need my column. The column here may not be just the data out of a single column. This could be a calculated value. Okay? This could be a concatenated value. Therefore, if I'm going to group data based on this, I might as well need to be able to do what? Calculate and see what that value is. Okay? Now, at this point, we don't look at the physical values of the column for the formatting aspect. Again, we're looking at these values for the way the execution is happening, because remember, all of the execution is based on the columns. Okay? So, if there are dependencies on what I need to do as far as the grouping is concerned, and I know based on the stats how the grouping works, then I can go from step 2 to step 3. If the grouping is not straight out of the table and there is a calculation and a little bit more complex, then we may actually do this third and then do this 1/4. Let me use a different color. So, if there is no calculation and every column value is straight out of the table, then based on the values we can estimate the grouping. So grouping may execute, and then the select, and then finally we come back and grab the final result of the table and order by them. However, as I mentioned to you, if the query is complex, if there are calculation involved, okay, then the order must change, because now before I can do grouping, I must perform the calculation. So once the data is retrieved based on the from and the where clause, then I may come here to do the calculation for the data and then go here for the grouping process. However, the order by is always the last thing that executes in the normal SQL statement. The only thing that executes after the order by is the fetch statement, which was added to Oracle Database 12c SQL for being able to return order data. Because prior to having fetch, if we wanted order data, we had to use views to sort data first and then select the results from the view. Now with the fetch executing after the order by, then we can order the data first and select the result set. So, as you can see, there is a rationale walking through and generating and looking at all the possible ways that I can satisfy this query. All of those information is based on that metadata and reviewed by the optimizer. So, once the optimizer is done with all of that work, then it will look at the plans that it has come up with. Between those plans, based on the resources that are available, both in the session and in the SGA for my database, and based on the size of the data, it then decides which one of those plans would be best. Optimizer always tries to choose a plan that is going to consume least amount of resources. We represent resources by a statistics that is called the cost. However, if the resources are available, then might as well use the resources and get the plan faster. Therefore, plan generation is not always just about the cost. It is also about what resources are available, because from time to time, optimizer may not choose the lowest cost plan. So, optimizer performed the work and has now generated the plan. Guess what? Run says this select statement. After I get the data, I read part of the data, I forget part of the data, right? I may execute the same select statement again. Not just me. Other sessions may also execute the same select statement. And as we said, generating execution plan can be very costly. So, once an execution plan is generated, we have another structure here in the shared pool that is called the library cache. This is a library of all execution plans that have been used within the database that we have been able to keep within the memory. Okay? Remember, as the plans are not used, we may phase these plans out to make room for new plans coming in. Now, inside this library cache, we have two components. Component number one is called the SQL area. This is a location where we put our SQL cursors for the sharing of the sessions. The second component here is called the PL SQL area. And as you all know, PL SQL is programming language SQL. We use it to be able to perform much higher functionality that is very limiting to be performed within SQL. Being able to use the data set in much more advanced formats and ways. And at the same time, I can have SQL statements in there that can be reused. All PL SQL in the database are pre-compiled, and we store the compiled version of the PL SQL. Therefore, when you access it, we load this compiled version here in the PL SQL area. All right? So now I have my plan in the shared area. That's the first place the plan is going to go, and the information about the plan is going to go, because while I'm executing, other users may need that same information. And as I told you, a copy of that cursor is also sent to my session. So now my session also has that same execution plan, that same cursor information, and can use that plan for execution and retrieval of the data. Once the plan is given to my session, then the server process that we talked about, that is assigned to each session, and we said it performs all the work on behalf of the users. So now, this server process is going to go down here into the data files based on the execution plan, get the data from these files, no matter where they're located, and bring that data up. Now, once we bring the data up, would other people need to use that data? Well, we said that data is stored in a logical format. The smallest logical unit of data for Oracle is called an Oracle block. So if I draw a block here for you, an Oracle block has a header and a body. In the body, we put rows. In the header, we have pointers that will tell me where each row starts. Okay? So now, when the server process goes to the data file to get the data, behind the scene, the engine has the pointers to how this logical data, which is based on rows, are stored within these data files. These chunks of data is then read from these data files that are associated to that table space and the object, and then this block is put together. And as you can see, normally we design our object and our blocks that can hold multiple rows. So if Ron's record is record number 2 here, then John's record could be record number 4. Therefore, if I read this block, which is Oracle's smallest I/O data, okay? So, since this block is the smallest piece of an Oracle data, once this block is put together, I might as well put this block in a shared memory so other users can get access to it in case John also requests a record and his record is record number 4. Therefore, right here in our shared memory, we have a structure that is called the database buffer cache. And we always show this database buffer cache in little squares. Now, can most of you guess why do we use these little squares to show the buffer cache? For those of you who guessed, you're absolutely right. Each one represents an Oracle block. These logical blocks. And we refer to these blocks as buffer pages. So, now the server process has gone to the data files using the plan and the engine behind the scene, located all of the blocks that it needs for my query, brought those blocks and loaded them into the buffer. So let's call this my read block. Okay? So actually, let me clean that up so you can read it a bit. One of my old friends had told me that in my past life I was a doctor. That's why my handwriting looks like prescriptions. Okay? Hopefully you got a chuckle out of that. I thought it was funny. Let's call this our read block. We load the read block over there. But now, I need to open this block and get out the rows and work with those rows to figure out calculations, to figure out values, to figure out groupings. So where do we do that? That is a private work. The only place that this block is opened and the rows become visible is in the work area. Okay? This will keep all the data private to the user. Because if this session is for Ron and Ron is accessing record 2, John may need record 4. Therefore, John is going to open this block in his own session and take out record 4. Ron is going to open the block and take out record 2. So we take the read block from here to the work area. And then here in the work area, if this was the block, we will open the block, open it, not just a lock, right? But opening itself, take out the rows, and then do whatever we need to do with the rows here. Once the work is done, we take the result set and we send it back to the user. So now, as you can see, we are done with a select execution. And as you noticed, to execute the select statement, all I need is the shared pool, the buffer cache, my data files, the server process, parser, and the optimizer. I don't need anything else here. Nothing else is involved in a select statement execution. However, as you all know, select is not just the only thing that we do. We also perform DMLs. When we perform DMLs, we are actually changing data. Okay? So, next, let's move on to a DML. Let's see how things change. If we change this select statement and make it an update. All right, so here is an update. Of course, the rest of the code will also change. Okay, you all know we do an update to a table, okay, and then set values. So we would say update HR.employees, and then set, for example, salary times 3, right? Ron deserves a raise, maybe? Just a joke, okay? Anyway, so coming out here, we can take a look at a DML statement. First has to retrieve a block, okay? Now, why do I need to retrieve a block? What if the statement is an insert? If the statement is an insert, I'm putting a new row in the database. Therefore, why do I need to read a block? Well, if you remember, we answered that question earlier. We want to keep data as compact as possible. Therefore, when you insert, if I have a block that is half used and the block is still open for inserts, I want you to insert your row in here. I don't want you to put it in a new block, because now when I read your row, I have to read an independent block. If I put your row here, then whenever I read your row, I got access to the rest of these rows too. That would make us a lot more efficient. Therefore, even in insert, we still have to return a block to the session to be able to insert a row in it. Therefore, update, insert, delete does not make any difference. We need similar operation. We need to get a cursor. We need to get an execution plan. We go to syntax and semantic check. Optimizer will generate a plan, so we get the read block, and we put the block here. So now, this is the block we read because either the row that I want to change is located in there, or I'm putting a new row in there. Okay? So now, either way, change a row, put a new row, delete a row. I cannot get rid of the read block. Why? Because in Oracle, most changes are done in 2 operations. Operation number 1, you change the data. Operation number 2, you perform a commit to validate the data is good and make the data permanent. This way, when you change data, we can lock up the row at the row level. So Ron can change row number 2, John can change row number 4. This way, users don't block each other, unless if they are transacting on the same row. Therefore, when I make the change that is in my DML, I will have to now create a new version of this block. Okay? In this new version, I have changed row number 2. So here is row number 1. There is row number 2 that was changed. Row 3, 4, and 5. So now, this becomes my new block. Okay? And as you all know, we do row level locking. Since this row was changed, a lock is enabled. And when a lock is enabled, all that locking information is then up here in the header of the block. So that way, when anybody else wants to read this row and we see the lock, we can go to the header. We can see which session has the lock. If the user is retrieving this for the session, then the user can read that data, because the session information is up here in my transaction info. So up here is my transaction info. Okay? So this transaction info identifies the session that has the lock. Now, if other sessions going to read this record, who the lock does not belong to them, then this transaction information will point to the version of the block where the read data was. Okay? Since I haven't committed, any other user that wants to read data can only read the last committed data. That's why we have to keep both versions of the block. So over here, we open the block, we change the row, we create our new block, and now that I created this new block, I need to put this block back into my buffer. So let's say now this is my DML block. All right? So my session has now changed the block, and the DML has been performed on the row. However, the actual DML process is not done yet. Why not? Because when the user decides to keep the change, the user would then say commit. Commit means make data permanent and remove the lock. If we at the database level tell the user commit complete, to the user that means that that data change can never be lost and is now permanent. The only way I can make a data change permanent is by getting that data change into the disk. Because for data residing in memory in my buffer is very unsafe. If my server crashes, the first thing I lose is my memory and the buffer. Therefore, at the commit, a lot of write might have to take place. I really don't want the users have to wait for all of that I/O. Let's say you just submitted a statement that changed 1,000 rows. And there could be many read block and the DML blocks that we have to put into the disk. That's a lot of data that has to be written into the disk. Therefore, we want to make that I/O invisible to the user. If I want to do that, what do I need to do? I need to be able to create something that is small that I can use as a guide to recreate that transaction. If I create that something small, then small items can go into the disk very fast. And if I lose my instance, I can read that small formula and I can recreate the change. So what is that small tiny formula called? That small formula is called the redo entry. Okay? And exactly it's called redo because we use this to recreate the change. And to recreate the change, with this information, we know the row ID. Of course, we know both the new and old column values. Okay? We also need to know the time when the change happened. Okay? So, of course, there's additional information here to the redo. This is the minimal of the addressing that I need to identify what row has changed and what were the values that were changed to. Now, the only entity that knows the before and after value and has access to this row, because remember, the row is now locked into the session, is the server process that's managing the session. Since this server process has made the change, created the block, is the only one that knows before and after picture. Therefore, the redo is actually created here in the work area when that new block is built. And then the redo is then placed by that server process into the memory. Okay? Once that redo is put into the memory, then we can send a message to the user that now your DML, your update, your insert, your delete is complete. Remember, the lock is still on the row though. Okay? So, have a buffer that holds the redo entries. This buffer, of course, is called the redo log buffer cache. Okay? The redo, we call it the redo logs because it's the log of all of the changes. And They're located into that buffer. All right? So now the DML process is complete, and we've informed the user that your update is now done. So we keep the data in logs. As long as we can, we're going to try to keep this old and new data in buffer. Why? Because the user eventually has to do what? Release the lock and make a change. And when that happens, I need to go into the block and clean up the header of the block where all of the transaction information is. Get the row and unlock the row. And now remember, since 10G and up, we also, actually 9I and up, we have a retention on the old data after the commit. Okay? The old version of the data. Because if the user does not say commit, the user could say rollback. Rollback means my change is no good. Throw away the change and put back the original block. Okay? So whether it's commit that I got to do cleanup, or it's the rollback that I got to get rid of the new block and put the old block as the current valid block, all of that would then need my blocks in memory. That's why we try to keep it in memory as long as possible. All right? So next, the user will go in and say commit. Once the user say commit, as we said, if I can get this redo into the disk, then with that redo I can recreate the change. I can tell the user, commit complete, make sure to remove the locks here in memory. Okay? Once the lock in memory is removed, then now the rows can be read by the other users. Okay? So when the user say commit, we will update the list of all of the blocks that are locked up, because behind the scene, when the blocks get locked up, we keep a list of them. Okay? The list of the changed blocks. Then we go in and update the list of changed blocks to say this block was committed, and the timing of that commit that is now there would overwrite the locking that we have on the row. Okay? And we have a background process that is called the log writer. So when the user say commit or rollback, then the log writer fires, grabs the redo, and dumps the redo into a set of files we call redo log files. All right? Now, this redo log files, all of those redo that are here get dumped because the redos are small. When one user say commit, it is going to take me the same amount of time to dump this whole redo into the disk versus going in there and finding that one redo for the user that say commit to put it into the disk. Therefore, when a user say commit, okay, or anything in the database issues an internal commit, all right, the log writer will then fire and dump the redos into the redo log file. Now, what happens if nobody commits or does anything that would generate an action to dump the redo? Can I keep that redo in the buffer indefinitely? The answer is no. Why not? Because if I keep the redo here, this redo and the row IDs are a guide of what blocks are here. So if I don't write this redo and wait only for the user to say commit, imagine what happens if user's transaction is changing 100 million rows. Then it would fill up my whole buffer, and that transaction may not finish. Okay? That's why normally we do commit in the middle of big transactions. Okay? Not just for the memory management, but also for transaction management. However, Imagine the same way that I can have many rows transacted on, there could be 1,000 users connected to the database who each change 10 blocks. All right? Now you got the whole buffer locked up, and nobody else can ever read data because now the buffer is full of changed blocks. Therefore, in Oracle, we may not wait for the commit to write the change blocks into the disk. However, since the redo is used as a guide to know which blocks have to be written into the disk, the redo is also dumped into the disk periodically. If no action fires the redo to be dumped, we will fire an internal action every 3 seconds of log writing. This is not 3 seconds of real time. Many users always confuse that, and they go take a look at the database and say, hey, we haven't wrote any data for the last 20 minutes. That is correct. Why? Because you haven't done 3 seconds worth of the redo. If you haven't done 3 seconds worth of redo, there is not enough changes in the buffer for me to worry about to write them into the disk. Therefore, the 3 seconds that automatically fires the redo writing into the redo log file, that's 3 seconds worth of log writing. Because if you have 3 seconds worth of log writing, that could mean a lot of blocks are pending. Okay? So now, we write the data into the redo log file. So, sometimes, as we just said, the changed blocks go to the disk after the commit that fired these redos into the redo log files. Sometimes I fired the commit. The redos got dumped. John's commit that wasn't even, John's change that wasn't committed may also be written into the disk because all the redos were already written into the disk. Okay? So, to write the blocks into the disk, we have another background process that is called the database writer. Okay? So the job for database writer is to write those change blocks into the disk. Therefore, the read block would go back into the disk, okay, down here, into a location we call undo. Why do we write it in the undo? Remember, Ron issued the commit, caused all the redo to go to the disk. John's change was also here. That got written into here. So now, John's blocks are written into the disk. But John hasn't committed yet. Therefore, if I don't keep the old read block, later on, if John says roll back, I don't have the old block to put back in. That's why we write the old block into undo. So we can undo a change on rollback. So remember, undo, redo are not the same thing. Undo is used for rollbacks. Okay? Redo is used in case of an instance crash for the recovery of the instance and the changed blocks that may not have gotten into the disk by the database writer. Everybody follow? As you know, log writer fires first, writes the changes. Data writer fires next to write the change blocks. If in between the two my database crashes, the redos here can then be used to recreate the change. However, once the database writer writes the changes into the disk, I don't need that formula anymore because the user's change is now saved. Therefore, Oracle can write over the redo. So we manage our redo into groups. So Oracle write into group 1. When group 1 gets filled up, it can switch to group 2 and write into group 2. While log writer is writing into group 2, then DB writer can use group 1 as a guide and write the changed blocks into the disk. All right, that's why redo is managed in groups. So here's group 1, group 2, and group 3. So we have 3 groups showing here. Now, if I lose any of that redo, if any of them are damaged, my instance crashed, now the user data is gone. So I don't want that ever to happen. Therefore, we multiplex the redo groups. So we keep multiple copy of the file in each group. So for example, if I have 3 copies of each group, here my group 3, that's the inner group, will have copy, let's say 3A, 3B, and 3C. Having each one of those on a different storage location, even if 2 of them get damaged, I still have 1 more. Therefore, I would never lose the end user data. Okay? That's why the groups are multiplexed. If you have external redundancy, we recommend 2 redundant members. If you do not have external redundancy, then we recommend 3 redundant members for each group. And number of groups. 2 groups is a minimum for the Unix-based and the Linux environment. 3 groups are the minimum for Windows. However, as you know, you never want to run with minimums, because if one of those groups gets damaged, then your changes are going to hang, because we cannot write redo. Therefore, we always recommend minimum 3 groups for the redo. Personally, I many times recommend to my clients up to 5 groups. This way, I can afford to lose 2 groups, and my database still has 3 groups for normal operation, and possibility of hanging is much less. Therefore, I am fault tolerant. Everybody follow? Very good. So now, the log writing has written the redo. The database writing has written the changes, the old value into undo. And then the new block will be written by the DB writer into the actual data file. Where that block and the row existed. Okay? So now, DML operation, retrieve the block into memory. From memory, took it to the work area, created the new block after the change, put the new block in memory, both versions exist there, created the redo in case of to manage failures, put it into the redo log buffer. Then, when the time comes, either the sessions say commit, other people say commit, or happened at 3 seconds or database options, the log writer will fire and dump the redo into the disk. Once the redo is into the disk, on the next writing, the database writer will then use the redo as a guide and writes the changed blocks into the disk. The new block into data file and the old block into undo. And finally, the transaction work is now complete. So now, as you can see, for performing the DML, now we had to bring in the log buffer. We had to bring in 2 writers to perform and manage these changes so they are not lost. What is next is filling up the rest of this empty space that we still have left over. Of course, there are some components here that we still want to talk about to finish up this architecture. We're going to take a short break. We will come back and finish up this configuration.